Hi, and welcome back to statistics. All right, so we just found out that we can do inferences, which means we can talk about something about the population based on a sample. So that's what's really powerful about statistics. So that's what we're going to really get into today. So in this lecture, we're going to talk about one thing called a point estimate. It's a single value or point used to approximate a population parameter. So for example, we're not going to be able to find mu, right, the entire population of the salt amount in the ocean, but what we can do is find x bar. So x bar is a point estimate for mu. It approximates the population mu. And beyond that, we're going to find something called a confidence interval. So confidence interval is another way of estimating the mean, but instead it consists of an interval. So two numbers, a minimum and a maximum, that's obtained from our point estimate, and a percentage that says how confident we are that the parameter is actually in there. But, you know, we've done this before. But as we move on, we're going to find that a confidence level, that percentage, is the probability 1 minus alpha that the confidence interval actually does contain the population parameter. Our most common ones are 90, 95%, and 99%. If we wanted to know alpha, 90%, if we have that as our confidence level, then alpha would be 10%. It's what's left over. If our confidence level is 95, alpha would be 5%, and if 99%, then alpha is 1%. So it's what's left over in that percentage. When we go toward interpreting confidence intervals, we must be very, very careful. So for example, if we had an interval between 20 and 40, and we're saying that mu lives somewhere between 20 and 40, what we're saying, we are 90% confident that 20 to 40 actually does contain the true value of the population mean. We're not saying that there's a 90% chance that 90% of the means would fall in there. No, because we're saying that mu would actually fall in there, and we're 90% confident for that. So basically that means that if we take a sample after sample of sample, and they're all the same size samples, and we find this confidence interval, 90% of them would contain the value of our population mean. So for example, we find x bar, and we are going to add and subtract something, and so that we get our minimum, we get our maximum, minimum, maximum, minimum, maximum over and over and over and over again. If we do a 90% confidence, that means 9 out of 10 of them would actually contain mu, something that we don't know what it is. But we've done this before. In fact, our favorite one has been the 95%, because we know if our graph variable is normally distributed, 95% of our data is between two standard deviations. So if our mean's there, this is mu minus 2 standard deviations, and this is mu plus 2 standard deviations. So let's see, for a sample of 20 people, the mean age that people try marijuana for the first time was 16. So let's see, we have two numbers. N is 20, because that's our sample size, and it says the mean age of those 20 people. And if this is our sample, that means our sample mean is 16. Assume that the population standard deviation is 4 years. So sigma is 4, population standard deviation. So that's going to be a key word to help us know what to do. And that age is normally distributed. What is the point estimate for the mean age that people try marijuana? So remember what point estimate meant? Well, a point estimate is our x bar. So x bar is 16. That's the best we can do, because we can't ask everyone when's the first time that you tried marijuana, right? And plus, people probably wouldn't be honest. So x bar is 16. Now we're going to find a 95% confidence interval for the mean age that all people in the U.S. try marijuana for the first time. So think of what we just talked about. That's 95% if it was mu. We'd add and subtract 2 standard deviations. But we don't know mu. We know x bar. So what we're going to do is we have to turn everything into x bar. So we're going to take x bar and we're going to subtract 2 standard deviations. But remember, if we don't know if this isn't mu, then we have to change everything into x bars. So this is exactly what we've talked about in the previous section. All right, so here we go. To find sigma of x bar, we know that it has to be normally distributed or a large enough sample size. Age is normally distributed. So we know that sigma over the square root of n, sigma in this case is 4. The square root of n, and n is 20. So we take our handy dandy calculators, 4 divided by the square root of 20, and we get 0.8944. I'm going to take my mean, 4, whoops, not 4, 16, good grief, 16, and I'm going to add and subtract 2 of my sigma of x bars, so 2 times 0.8944. So that's 16 minus 2 times 0.8944, being careful about our order of operation. So remember, we multiply first and then we subtract if you have an older calculator. And we would get 14, and then 16 plus 2 times 0.8944, and we'd get 17.7888. So we know that basically this is saying that we are 95% confident that the mean age of all people in the U.S. that have tried marijuana for the first time, their age would be somewhere between 14.2 and 17.8 years. Let's do another one. The following data gives the additional sleep in hours obtained by a sample of 10 patients. So we know I lost my pen. N is 10. Using a new sleeping drug, assume additional sleep is normally distributed. It has a population standard deviation of 0.5 hours. So that's my sigma, population standard deviation. So what is my point estimate of the mean additional sleep? Well, I don't know what mu equals, so the best I can do is find what x bar equals. And in order to do that, we're going to go to StatCrunch. So here I go. I'm going to move that over. I'm going to get that. And this is my additional sleep. And hopefully I can see that. That's really tiny for me. So I'm just going to put my data into one column, and I see that I do have negative values and positive values. And so thinking of that, remember this is additional sleep, so I guess negative values would indicate that we're losing sleep in that case. Positive values means that we are getting sleep, adding sleep. Okay, to find the mean, I go to Stat, Summary Stats, Columns. I find my additional sleep. All I need is that mean. Click Compute, and I get 2.33. Okay, back to this, 2.33. And now I want to find a 95% confidence interval for the mean additional sleep obtained by all people using the new sleeping drug, using my point estimate. So I'm going to take my mean, and I'm going to add and subtract 2 of my standard deviations. But since I'm dealing with x bar, that means I've got to change this into sigma of x bar, which is sigma over the square root of n. And in this case, n is 10. N is 10. That's kind of fun to say. So I get 0.1581. So here I go, 2 times 0.1581. And again, remember that I'm going to multiply first, depending on my calculator. So I should get 2.0138. And if I add it, then let's see what would it get. I'd get 6462. So this says that I'm 95% confident that the mean additional sleep we're going to get is between about 2 hours to a little over 2.5 hours. And I don't know about you, I could have used 2 hours of additional sleep last night. Oh, so tired.